Imagine floating in the endless black of space, surrounded by silence until suddenly, a faint but unmistakable signal hums through the void. No, it's not from a distant star or a passing satellite. This signal comes from something far stranger, an interstellar comet, a wanderer from another star system, whispering secrets we're only beginning to decode. These cosmic travelers don't just shine silently as they streak past our sun. Some of them emit signals, radio waves, bursts of energy, patterns that defy explanation. And the most unsettling part, we have no idea what's causing them. Interstellar comets are rare, fleeting visitors from beyond our solar system. Unlike the comets we're familiar with, born from the icy edges of our own cosmic neighborhood, these drifters come from places we can barely fathom. They carry the chemistry of alien stars, the raw ingredients of worlds we'll never see. But when some of them pass through our corner of the galaxy, they don't just leave a trail of ice and dust, they broadcast something. Signals pulse from their cores, flickering like Morse code from the depths of space. Scientists have catalogued 25 of these bizarre transmissions so far, and each one deepens the mystery. Some repeat at odd intervals, others vanish as suddenly as they appear. A few even seem to change frequency, as if whatever's sending them is adjusting. What could possibly be generating these signals? Natural phenomena, some unknown chemical reaction in the comet's tail, or could it be something more? The truth is, we're staring into the dark with more questions than answers. These unexplained transmissions challenge everything we think we know about comets and maybe even about life itself. Today, we're diving deep into all 25 of these enigmatic signals, unraveling their secrets one by one. By the end of this journey, you'll see the cosmos in a whole new light, and you might never look at a shooting star the same way again. So buckle up, the universe is about to get a lot stranger. The very first signal that shook astronomers wasn't just unusual, it defied every expectation. It came from an interstellar comet designated as C/2017 U1, the first known visitor from another star system. As telescopes tracked its high-speed journey past the sun, something extraordinary happened. A burst of radio waves, sharp and sudden, crackled through the silence. Unlike the predictable static of solar wind or the steady hum of cosmic background radiation, this signal pulsed at 442 MHz, an unnatural-seeming frequency with no obvious cosmic source. What made it even stranger, it lasted exactly 73 seconds before vanishing without a trace. At first, researchers assumed it was equipment malfunction. But when multiple observatories from Arecibo to the Green Bank telescope confirmed the detection, the real mystery began. Natural explanations fell short. Solar flares couldn't explain the precise frequency. Chemical reactions in the comet's tail, unlikely. The energy output was orders of magnitude too high. One theory suggested piezoelectric effects, where stress on icy minerals could generate electric charges, but nothing in our solar system's comets had ever produced signals like this. Then came the wilder hypotheses. A few astronomers cautiously floated the idea of artificial origins, not necessarily aliens, but perhaps an unknown technology we hadn't considered. The signal's abrupt start and stop, its narrow frequency band, even its eerie symmetry, all hinted at something engineered. Of course, skepticism ruled the day. But one thing was undeniable. This was humanity's first tangible encounter with an interstellar object that didn't just pass through silently, it spoke. And we still haven't deciphered what it said. But the mystery of that first signal didn't end with its sudden appearance. When astronomers reanalyzed the data months later, they found something that sent chills down their spines. Hidden beneath the noise was a pattern. The signal hadn't just been a random burst. It repeated faintly but unmistakably at intervals of exactly 11 minutes and 42 seconds. 3 more times, the same frequency pulsed out into the dark, each burst identical in length and strength before vanishing for good. This wasn't the erratic crackle of space weather or the chaotic spray of a comet's tail. It was rhythmic, almost deliberate. The scientific community split into warring camps over what this meant. Mainstream researchers argued for exotic but natural explanations. Perhaps the comet's rotation triggered periodic bursts as its icy surface fractured under the sun's heat, or maybe interactions with solar magnetic fields created a resonance effect. But the timing was too precise, the repetition too mechanical. Even more baffling, the signal's frequency drifted slightly between bursts, as if whatever was generating it was moving or being adjusted. Then came the real curveball. When researchers compared the signal's modulation to known cosmic phenomena, nothing matched. Not pulsars, not magnetars, not even the eerie echoes of black holes. It was as if the universe had handed scientists a riddle wrapped in an enigma. Some dared to whisper the unthinkable. Could this be a beacon, a malfunctioning probe? The dying embers of some long-lost technology. Of course, extraordinary claims require extraordinary evidence, and no one was ready to jump to conclusions. But one thing became clear: this wasn't just a fluke, it was a clue, and as more interstellar comets whispered their cryptic signals across the cosmos, the puzzle only grew deeper. Whatever's out there, it's not playing by the rules we know. The second signal changed everything. Unlike the first's abrupt burst, this one was subtle, a whisper in the cosmic static that almost slipped past unnoticed. Detected trailing behind an interstellar comet catalogued as 2,018X3, the transmission was so faint it flickered at the very edge of detectability. At first, researchers dismissed it as instrument noise, but then, over 17 agonizingly quiet nights, the same pattern crept back: 90 seconds of ultra-low frequency radio waves, repeating every 6 hours and 19 minutes like clockwork. What made this signal extraordinary wasn't just its persistence, but its structure. When amplified and filtered, the data revealed a series of modulated pulses, rising and falling in intensity with mathematical precision. It wasn't random, it wasn't chaotic, it bore the hallmarks of a repeating sequence, almost like a heartbeat. Scientists scrambled to explain it. Could it be the comet's rotation periodically exposing an electrically charged surface to solar wind? Maybe, but the timing was unnervingly exact, and the signal's frequency range defied natural explanations. The real challenge, studying it before it vanished. Unlike solar system comets that linger for months, interstellar visitors streak through at breakneck speeds. Teams worldwide coordinated desperate observation campaigns, diverting telescopes from planned projects. The Green Bank Telescope in West Virginia operated at maximum sensitivity, its massive dish straining to catch whispers from the void. The European VLBI network combined data from 12 radio telescopes across continents, stitching together fragments of the signal like archaeologists reconstructing a shattered artifact. Then came the breakthrough, or perhaps the deeper mystery. When researchers superimposed all detected pulses, they found something chilling. The signal wasn't just repeating. It was evolving. Each cycle introduced minute variations, as if whatever produced it was learning, adapting, or responding. The implications sent shockwaves through the astronomy community. Natural phenomena don't refine their behavior. Machines do, life does. Yet before anyone could draw conclusions, the comet plunged beyond Jupiter's orbit, its signal fading into the noise forever. All that remains is the data, and a question that haunts every scientist who studied it. Was this the cosmos playing tricks, or were we listening to something far more profound? The universe rarely gives easy answers, but sometimes it offers whispers, and those whispers can rewrite history. When astronomers first grappled with Signal 2's rhythmic pulses, their immediate instinct was to search for natural explanations. After all, the universe is full of strange but ultimately mundane phenomena: cosmic static, magnetic field fluctuations, even the groans of dying stars. Could this signal be another quirk of physics, something extraordinary but not necessarily alien? The leading theory pointed to solar wind interactions. As charged particles from the sun bombard a comet's surface, they can excite molecules in its coma, producing faint radio emissions. But here's the problem. Those emissions are typically broadband, chaotic, and unpredictable. Signal 2 was none of those things. Its razor-sharp frequency and clockwork repetition bore no resemblance to the messy, scattered bursts solar wind usually generates. Then there's the outgassing hypothesis. When comets heat up near the sun, volatile compounds like carbon dioxide and methane erupt from their surfaces in dramatic jets. These eruptions can create plasma clouds that interact with solar magnetic fields, potentially emitting radio waves. But again, the details didn't align. Outgassing signals are transient and irregular, flaring up and fading without pattern. Signal 2's 90-second bursts, arriving precisely every 6 hours and 19 minutes, suggested something far more structured, like the steady ticking of a cosmic metronome. The most tantalizing natural explanation came from a team at Caltech who proposed the idea of electromagnetic tethering. Imagine the comet's nucleus as a spinning, lopsided ball of ice and rock. If it contained conductive minerals, say iron-rich dust, its rotation through the sun's magnetic field could theoretically generate currents, turning the entire comet into a rudimentary dynamo. These currents might then pulse periodically as the comet tumbles, creating something akin to a natural radio transmitter. It's a brilliant idea, but the math doesn't quite add up. For one, the signal's frequency drift. Those slight but measurable shifts between bursts would require the comet's rotation to speed up and slow down in impossibly precise increments. Even stranger, the signal's modulation suggested harmonics, overlapping waveforms that don't occur in simple natural systems, perhaps the most damning evidence against purely natural origins. The signal's evolution. Over those 17 nights of observation, the pulses didn't just repeat, they adapted. Minor variations in duration, subtle shifts in frequency modulation, even what appeared to be nested patterns within the main sequence. Nature doesn't refine its signals, a pulsar doesn't tweak its rhythm, a magnetar doesn't adjust its output, but technology does, life does. That's not to say the signal was definitively artificial. Science demands caution, and extraordinary claims still require extraordinary evidence. But as each natural explanation crumbled under scrutiny, one unsettling truth became harder to ignore. Whatever produced Signal 2, it operated by rules we don't yet understand. And that's where the real mystery begins. Signal 3 didn't announce itself with a dramatic burst or a rhythmic pulse. It slipped into existence like a shadow crossing a doorway. Detected by the Deep Space Network's antennas in late 2021, this transmission originated from an interstellar comet so distant it was little more than a speck in the void. At first, it barely registered a faint, narrowband signal hovering around 1 GHz, almost indistinguishable from the background hum of the cosmos. But within hours, astronomers realized this wasn't just noise. The signal carried a peculiar structure, a series of rapid oscillations that resembled something. A pattern, a distorted message, or just the universe's latest cosmic prank. Then, after 48 hours of meticulous tracking, the unthinkable happened. Signal 3 didn't fade or distort, it vanished. One moment it was there, pulsing weakly but persistently. The next, absolute silence, no gradual decay, no interference, no technical malfunction to blame. It simply ceased, as if someone or something flipped a switch. The suddenness was as shocking as the signal itself. Natural phenomena don't just stop. Solar winds taper off, cometary outgassing sputters, even dying stars flicker before they go dark. But this was like a radio station cutting mid-broadcast, leaving astronomers clutching their headsets in disbelief. Theories erupted like solar flares. One faction argued the signal was a rare but natural plasma echo, a fleeting resonance caused by the comet's ionized tail interacting with interstellar magnetic fields. If the geometry shifted even slightly, the effect could collapse instantly, explaining the abrupt cutoff. Others pointed to the possibility of occlusion. Perhaps the comet passed behind a dense cloud of cosmic dust, blocking the signal entirely. But follow-up observations ruled that out. The line of sight remained clear. The most unsettling hypothesis came from a small group of researchers who noticed something eerie in the signal's final moments. In the last 20 seconds before disappearance, the oscillations shifted not randomly, but in a way that mirrored error correction protocols used in human deep space communication. A coincidence, probably, but the implication was hard to ignore. What if the signal wasn't just stopping? What if it was being stopped? Could it return? That's the question haunting astronomers today. Unlike signals 1 and 2, which followed discernible patterns, 3's behavior offers no clues. Some argue it was a one-time event, a cosmic glitch we'll never witness again. Others speculate it might be cyclical, reactivating when or if the right conditions align. There's even a fringe theory that the comet isn't the source at all, but merely a relay, bouncing transmissions from something else entirely. For now, all we have are questions and a graveyard of unproven theories. But one thing's certain: when the universe speaks, it doesn't owe us an explanation. And sometimes the most chilling message isn't a sound, it's the silence that follows. Signal 4 didn't just crackle or pulse, it sang. When astronomers first picked it up in early 2023, the transmission stood out not for its strength or repetition, but for its eerie, almost musical quality. Originating from Interstellar Comet 2022E3, the signal consisted of multiple frequencies layered together in perfect mathematical harmony, a chorus of tones resonating at precise intervals. This wasn't the chaotic static of plasma or the monotone drone of a pulsar. It was a symphony of frequencies, each note locked into place with unnatural precision. The discovery sent shockwaves through the scientific community because harmonic signals like this simply don't occur naturally in space. When cosmic objects emit radio waves, they're typically messy, broadband affairs, smeared across the spectrum by turbulence and magnetic fields. But signal 4, it was clean. Its primary frequency sat at 666 MHz, flanked by 2 secondary tones at exactly 1/3 and 1/5 of that value, a perfect harmonic series. Even more baffling, these frequencies shifted in unison, maintaining their ratios as the comet sped through the solar system. No known physical process in nature behaves this way. Theories exploded like supernova. Some researchers pointed to exotic chemistry, suggesting the comet's unique composition, perhaps laced with superconducting minerals, could create resonant cavities that amplified specific frequencies. Others proposed a bizarre magnetic interaction where the comet's icy nucleus acted like a tuning fork, vibrating in sync with the sun's magnetic field. But the math never quite added up. Natural harmonics are never this precise, and they certainly don't stay precise across millions of miles of space. Then came the hypothesis that split the room. A team at the SETI Institute ran the signal through their analysis pipelines, comparing it to known artificial transmissions, human satellites, deep space probes, even historical attempts at interstellar messaging. The result, Signal 4's harmonics bore an uncanny resemblance to phased array antenna patterns, the kind used in radar and long-distance communication. Not identical, but close enough to raise eyebrows. Could this be some kind of beacon, a malfunctioning relay, or worse, something that wasn't malfunctioning at all? Skeptics rushed to debunk the idea, arguing that coincidence isn't evidence. Yet even they couldn't ignore the signal's most unsettling feature, its stability. For 17 days, as the comet hurtled past Mars and into the outer solar system, the harmonics never wavered. No drift, no distortion, just that same unbroken chord resonating across the void. Natural phenomena flicker, they fade, they change. Signal 4 didn't. It was as if whatever produced it was designed to endure. By the time the comet vanished beyond Neptune's orbit, the debate had reached a fever pitch. Were we listening to the universe's most elaborate cosmic accident, or something else entirely? The answer, like the signal itself, remains just out of reach. But one thing's certain, the cosmos has a new soundtrack now, and it's playing in perfect tune. Signal 5 wasn't subtle, rhythmic, or musical, it was violent. Unlike the eerie precision of previous interstellar comet transmissions, this one announced itself with raw, unfiltered power. First detected by the Parkes Observatory in Australia during a routine sweep, the burst slammed into receivers like a cosmic sledgehammer, a single pulse of radio energy packing more intensity than the average solar flare. And then, just as abruptly as it arrived, it was gone. No follow-up, no warning. Just a 9-millisecond blast of energy so concentrated it briefly overloaded the telescope's sensors. What made Signal 5 truly baffling wasn't just its strength, but its randomness. Over the next 6 months, astronomers caught it 7 more times, always from the same interstellar comet, 2023R4, but never at predictable intervals. Sometimes weeks passed between bursts, other times 3 would strike in a single day. No celestial clockwork here, no harmonic patterns, just chaos. Teams at the Very Large Array in New Mexico and China's Fast Telescope synchronized observations, desperate to catch the signal in the act with multiple instruments. Yet every time they thought they'd pinned down a pattern, Signal 5 defied them. Theories struggled to keep up. One camp proposed cryovolcanic eruptions, explosive jets of superheated ice and gas erupting from the comet's subsurface oceans. On icy moons like Enceladus, such eruptions do produce radio static, but nothing approaching Signal 5's raw power. Another group pointed to relativistic electrons trapped in the comet's makeshift magnetosphere, suggesting their sudden release could generate bursts. But detailed modeling showed the energy requirements were off by orders of magnitude. Then came the observation that changed everything. During the 5th detected burst, the European Space Agency's Mars Express orbiter caught something the ground telescopes missed: a flicker of X-rays accompanying the radio pulse. Not scattered radiation, but a tight beam perfectly synchronized with the main signal. That wasn't natural. Natural processes don't coordinate emissions across multiple wavelengths with millisecond precision. The discovery sent researchers scrambling. Some began whispering about directed energy, the hallmarks of a system focusing its output, not spewing it randomly into space. Yet for all the speculation, the comet offered no answers. As it receded into interstellar space, Signal 5's bursts grew fainter, then stopped entirely. No finale, no grand revelation, just silence. Today, the data sits in observatory archives, a cosmic riddle wrapped in static. Because here's the terrifying beauty of it: if this was artificial, its creators didn't want to be understood. They, or it, left no manual, no repeating code, just a series of screams across the dark, and we may never know who was listening. Signal 6 didn't just whisper or scream, it spoke in stereo. When astronomers first tuned into this transmission from Interstellar Comet 2024b9, they didn't find a solitary frequency or even a shifting harmonic. Instead, the signal pulsed on 2 completely distinct wavelengths simultaneously, 820 MHz and 1.4 GHz, locked in perfect synchronization. Dual-frequency emissions aren't just rare in nature, they're practically unheard of. Cosmic phenomena don't broadcast on multiple channels at once, but this comet did, and that defiance of expectations sent researchers spiraling down a rabbit hole of theories. The moment the dual frequencies registered, observatories from Chile to South Africa scrambled to confirm the finding. Cross-referencing data from the Atacama Large Millimeter Array and the Mercator telescope revealed something even stranger: the 2 frequencies weren't independent. They modulated in tandem, rising and falling together as if yoked by some invisible force. Natural radio sources don't behave this way. Solar bursts scatter across the spectrum. Pulsars emit narrow bands, but signal 6. It was like listening to a duet where both singers moved in flawless unison, never missing a beat. Explanations flew fast and furious. One team proposed an unprecedented magnetic interaction. Perhaps the comet's nucleus contained twin plasma cavities, each resonating at a different frequency as solar wind poured through fissures in its icy surface. Another group suggested piezoelectric effects, where stress fractures in mineral-rich ice generated alternating currents at distinct vibrational modes. But simulations quickly exposed flaws in both ideas. Magnetic cavities would fluctuate wildly under solar pressure, not hold steady, piezoelectric responses. They'd produce messy harmonics, not clean, isolated frequencies. Then came the wildcard theory, beaming. If the comet wasn't generating the signals but reflecting them, could some distant source be deliberately targeting two frequencies at once? The concept wasn't entirely far-fetched. Human satellites use dual-frequency transmissions to combat interference, sending identical data streams on separate bands to ensure reception. Was this a natural coincidence or something more unsettling? The debate grew so heated that the International Astronomical Union convened a special session, with researchers trading barbs over coffee and slide decks. Yet for all the arguing, Signal 6 held its secrets close. As the comet retreated toward interstellar space, its twin frequencies never wavered, never crossed, never once fell out of sync. Then, without warning, they cut off together, mid-transmission, mid-pulse, as if a universal mute button had been pressed. No fade, no distortion, just silence where there had once been harmony. Today, the data sits in observatory archives, a paradox wrapped in static. Because here's what keeps astronomers awake at night. If this was natural, it redefines what nature can do. And if it wasn't, then someone or something just taught us a new way to listen. Signal 7 didn't just flicker or flash, it endured. While other interstellar comet signals lasted seconds, minutes, or at most a few weeks, this one defied all expectations by broadcasting continuously for 194 days. Detected in late 2024 from Comet 2023L5, the transmission wasn't particularly loud or complex, but its sheer stamina rewrote the rules of what we thought possible. Most cosmic radio sources fade as conditions change. Solar wind fluctuates, comets rotate, surfaces erode, but Signal 7, it clung to existence with eerie persistence, a whisper that refused to die. The signal's longevity alone would have been remarkable, but its behavior added layers of mystery. Unlike the chaotic bursts of Signal 5 or the harmonic precision of Signal 4, this emission was oddly monotonous. A steady, narrowband pulse at 418 MHz, varying in intensity by less than 2% over its entire 6-month lifespan. No drifting. No modulation, just relentless consistency, as if whatever produced it was shielded from the chaos of space itself. Scientists scrambled for explanations. The leading natural theory involved a freakishly stable cryovolcanic vent, a geyser of superheated ammonia or methane deep within the comet's nucleus, continuously ejecting charged particles into space. On icy moons like Triton, such vents can produce weak radio emissions, but nothing this sustained or precise. Another hypothesis pointed to a trapped plasma bubble, a pocket of ionized gas caught in the comet's magnetic field, resonating like a cosmic tuning fork. But plasma is turbulent by nature. It shouldn't hold a single frequency for more than hours, let alone months. Then came the curveball. Midway through the signal's run, India's giant meter-wave radio telescope detected a subtle anomaly, a 90-second gap in transmission, followed by an exact reset to its original frequency and intensity. Natural processes don't pause and resume like clockwork. Machines do. Systems with fail-safes do. The observation sparked heated debates. Could the comet be hollow, housing some kind of self-regulating mechanism? Or was the signal being relayed through it like a cosmic repeater station bouncing transmissions from an unknown source? As the comet drifted beyond observational range, Signal 7's final moments only deepened the intrigue. Instead of fading gradually or cutting out abruptly, it dimmed. Over 72 hours, its strength decreased in perfectly linear increments, as if someone or something was methodically turning down a dial. That level of control is alien to natural phenomena. Stars don't dim on timers. Comets don't shut off their emissions like engines cooling down. Now, with the signal silent and the comet lost to interstellar space, we're left with more questions than answers. Was this a natural wonder unlike anything in our solar system, or evidence that we're not just listening to comets but to something using them? The universe rarely serves up easy explanations. But when it offers a signal that outlasts half a year of scrutiny, it's telling us to pay attention. Signal 8 didn't just break the rules, it rewrote them. Unlike the chaotic bursts or steady hums of previous interstellar comet transmissions, this one arrived with a signature so bizarre it left astronomers questioning the very foundations of radio astronomy: near-perfect circular polarization. Detected in early 2025 from Comet 2024K7, the signal's electromagnetic waves didn't vibrate randomly or along a single plane like natural cosmic emissions. Instead, they spiraled through space like a corkscrew, their electric field rotating with clockwork precision. This wasn't just unusual, it was unprecedented. Only one other phenomenon in the known universe produces such pristine polarization: human-made radar. The moment observatories confirmed the polarization, the race was on to explain it. Polarized radio waves can occur naturally. Solar flares sometimes twist emissions slightly, and pulsars occasionally exhibit weak polarization. But Signal 8's 97% circular polarization was off the charts. Even the most extreme astrophysical objects like magnetars or black hole jets rarely exceed 40%. Teams from Jodrell Bank to the Very Large Array ran exhaustive simulations, testing every conceivable natural scenario. Magnetic field interactions: the comet's feeble field was thousands of times too weak. Plasma spirals in the coma. No known chemical mix could generate such clean rotation. Cosmic ray showers: the math collapsed under scrutiny. Then came the real head-scratcher. When researchers analyzed the signal's polarity over time, they found it wasn't just uniformly spiraling, it was switching. Every 11 minutes and 15 seconds, the rotation flipped from clockwise to counterclockwise, then back again, as if guided by an invisible hand. Natural processes don't toggle polarization with metronomic regularity. Machinery does, antennas do. The implication sent shockwaves through the scientific community. Some argued for an ultra-rare magnetohydrodynamic resonator, a hypothetical structure where the comet's rotation, solar wind, and magnetic fields aligned just right to create a natural polarized transmitter. Others pointed to the chilling precedent of human technology. Our own deep space probes use circularly polarized signals to maintain communication through turbulent plasma. Was this a cosmic doppelganger? Yet for all the theories, Signal 8 remained stubbornly enigmatic. Even as the comet faded into the interstellar dark, its polarized pulses never wavered, never degraded. Then, without warning or decay, they ceased, leaving behind a singular, unsettling truth. The universe, it seems, has a new way to scream into the void. And we still don't speak its language. Signal 9 didn't just broadcast, it evolved. Unlike the rock-steady frequencies of previous interstellar comet transmissions, this one refused to sit still. Detected from Comet 2025P8, the signal began as a humble 400 MHz pulse, unremarkable at first glance. But within days, astronomers noticed something unsettling. The frequency was creeping upward. Not in erratic jumps, but in a smooth, almost deliberate climb, as if someone were slowly turning a cosmic dial. Week by week, the signal drifted higher, eventually settling at 432 megahertz before vanishing. No comet in our solar system behaves this way, so what or who was tuning this transmission? The most immediate explanation seemed simple: the Doppler effect. Just as a siren's pitch rises as an ambulance speeds toward you, a comet's motion could theoretically shift a signal's frequency, but the math betrayed a problem. To produce signal 9's precise drift rate, the comet would have needed to accelerate at a constant rate for weeks, something physically impossible without an unimaginable external force. Comets don't have engines, they coast on gravity's whim, their speeds fluctuating subtly as they interact with planets and solar winds. Yet signal 9's frequency change was linear, as mechanical as a metronome. That left scientists staring down two possibilities. Either an unprecedented natural process was at work, perhaps the comet's icy interior was vaporizing layer by layer at an unnervingly consistent rate, altering the geometry of some hidden resonant cavity, or the drift wasn't caused by the comet's movement at all. Could the signal source itself be adjusting its output? The idea wasn't entirely fringe. Human satellites routinely tweak their frequencies to compensate for orbital dynamics. Was this a distant echo of similar logic? The debate grew even thornier when researchers discovered an anomaly in the drift pattern. Midway through the signal's 3-month lifespan, the frequency shift paused for exactly 48 hours, a hiatus with no corresponding change in the comet's trajectory or solar wind conditions. Natural processes don't take breaks, systems under stress don't arbitrarily freeze their behavior. Yet signal 9 did, as if waiting for some unseen cue before resuming its upward climb. By the time the comet retreated beyond observational range, the signal had left behind more questions than answers. Was this nature's latest sleight of hand? Or were we witnessing something far more unsettling, a transmission not just from the cosmos, but engineered for it? The universe, it seems, has a way of tuning its signals just beyond our understanding. And sometimes the most profound mysteries aren't in the message, but in how it changes. Signal 10 didn't just pulse or drift, it counted. When astronomers first locked onto this transmission from Interstellar Comet 2025 Q2, they expected another erratic burst or monotonous hum. Instead, they found something that defied all expectations: a precise, repeating sequence of radio bursts, each one a perfect echo of the last. 5 short pulses followed by 2 long ones, then a pause repeating in cycles of exactly 12 minutes and 7 seconds. This wasn't just noise, it was a pattern, a rhythm, a sequence, and in the vast, chaotic symphony of the cosmos, sequences like this don't happen by accident. The moment the pattern emerged, observatories worldwide went into overdrive. The Allen Telescope Array in California dedicated 70% of its dish time to tracking the signal, while China's FAST telescope isolated the comet's trajectory with military precision. What they found was chilling in its consistency. Over 3 weeks of observation, the sequence repeated 2,144 times without a single deviation. Not a missed pulse, not a shifted interval, just that same unbroken cadence: 5 short, 2 long, silence, repeat. Natural cosmic phenomena don't adhere to rigid templates like this. Solar flares stutter, pulsars waver, even the most regular astrophysical processes have margin for error. Signal 10 had none. Mathematicians quickly descended on the data, searching for hidden meaning. The sequence itself: 5 short bursts, 2 long, bore an eerie resemblance to prime number groupings, a pattern humanity has used in everything from ancient encryption to interstellar messages like the Arecibo broadcast. Was this a coincidence, a cosmic inside joke, or something far more deliberate? Researchers ran statistical analyses comparing the signal structure to known natural processes. The results were unambiguous. The odds of this pattern arising randomly were less than 1 in 10 million. Then came the real twist. Buried within the signal's modulation was a secondary layer, a faint but detectable shift in frequency between the long and short pulses. When graphed, these shifts formed a near-perfect Fibonacci curve, a mathematical spiral found in everything from galaxy arms to seashells. Nature loves Fibonacci sequences, but not like this. Not in artificial radio waves. The discovery split the scientific community into warring factions. One side argued for an ultra-rare resonant cascade, a theoretical scenario where solar wind excites multiple harmonic frequencies in a comet's plasma tail, aligning by freak accident into a temporary pattern. The other side pointed out the obvious: nature doesn't do temporary this well. By the time the comet vanished into the interstellar dark, the debate had reached a fever pitch. Because here's what no one could explain. On the signal's final day, the sequence changed. Not much, just a single extra short pulse inserted at cycle number 2145. A hiccup, a glitch, or something more unsettling, an adjustment. The universe rarely offers closure, but sometimes it leaves behind a pattern too precise to ignore. And this one's still counting. Signal 11 didn't just break the mold, it vaporized it. While most interstellar comet signals flicker at energy levels comparable to a handheld radio, this one arrived with the force of a cosmic lightning strike. Detected on September 12, 2025, from Comet 2025R9, the transmission packed more power in a single 3-second burst than our Sun emits across all radio frequencies in an entire hour. To put that in perspective, if Signal 6 was a whisper and Signal 5 a scream, this was a detonation. Energy levels spiked so high they momentarily blinded receivers at the Arecibo Observatory, leaving astronomers scrambling to confirm they hadn't witnessed an instrument failure or something far more unsettling. The sheer intensity of the burst defied every known comet-related phenomenon. Solar-wind interactions out of the question. The energy output was 1,000,000 times too strong. Cryovolcanic eruptions, not even close. Even the most violent outgassing events in our solar system's comets max out at kilowatt scales. Signal 11. It clocked in at petawatt levels, rivaling the output of gamma-ray bursts from colliding neutron stars. The only natural process that came remotely close was a theoretical magnetic reconnection event, where twisted solar magnetic fields snap and release catastrophic energy. But those occur near stars, not in the frozen hearts of drifting comets. Then came the real shocker. When researchers analyzed the signal spectrum, they found it wasn't just powerful, it was focused. Unlike the messy broadband static of solar flares or pulsars, Signal 11's energy concentrated into a razor-thin bandwidth at 895 MHz, with almost zero spillover into adjacent frequencies. That kind of precision doesn't happen naturally. In human terms, it's the difference between a wildfire and a laser beam. Theories veered into uncharted territory. One radical paper suggested the comet might have passed through a microscopic black hole, a hypothetical relic from the early universe whose Hawking radiation triggered an energy surge. Another team proposed an alien concept, a dark matter battery, where the comet's nucleus somehow catalyzed the decay of invisible particles into detectable radio waves. Both ideas stretched plausibility to the breaking point, but the alternative, that something inside the comet generated that pulse, was even harder to swallow. For 7 agonizing days, astronomers watched and waited, praying for a repeat performance that never came. Signal 11 remained a singular event, a flashbulb pop in the cosmic dark. Its aftermath left behind scorched circuit boards, shattered theories, and one indelible truth: the universe keeps weapons in its arsenal we haven't even imagined. And sometimes it fires them blindly into the void. Signal 12 wasn't just mysterious, it was invisible. Unlike the raw power of Signal 11 or the mathematical precision of Signal 10, this transmission played a cruel game of cosmic peekaboo. Detected on March 8, 2026 from Interstellar Comet 2025S3, the signal blipped into existence just long enough to set off alarms at the Deep Space Network's Madrid station, then vanished before any other telescope could confirm it. One moment, a clear pulse at 1.2 GHz, the next dead silence, no echo, no residual trace, just a single, fleeting whisper that left astronomers questioning whether they'd witnessed a revolutionary discovery or the ultimate glitch. The immediate assumption was equipment failure. Radio astronomy is notoriously finicky. Solar interference, atmospheric distortion, even terrestrial radio leaks can mimic cosmic signals. But the Madrid team ran every diagnostic imaginable. They recalibrated receivers, scrubbed data for electromagnetic interference, even checked nearby satellites. Nothing explained the blip. Worse yet, the signal's profile didn't match any known artificial source. Its frequency drift was too smooth for human satellites, its modulation too clean for random noise. It felt extraterrestrial, but without corroboration, it might as well have been a ghost. Then came the twist. 3 weeks later, the same comet passed within range of China's Fast Telescope, the most sensitive radio instrument on Earth. For 72 hours, astronomers trained its massive dish on the target, praying for a repeat. And for 72 hours, the comet stayed silent, not a flicker. Not a whisper, just the void's indifferent hum. The inconsistency split the scientific community. Half the researchers dismissed Signal 12 as a transient artifact, perhaps a rare atmospheric refraction bending a distant satellite's transmission into Madrid's path. Others pointed to an even stranger possibility. What if the signal was real but conditional? This wasn't entirely without precedent. In 2019, a team at the University of California documented ephemeral resonances, hypothetical zones where a comet's plasma tail could briefly act like a natural amplifier, boosting faint cosmic radio waves into detectable bursts. Under the right alignment of solar wind and magnetic fields, a comet might light up for seconds before fading back into obscurity. If true, Signal 12 might have been a cosmic mirage, a momentary lensing effect that vanished when conditions shifted. Yet the most unsettling theory came from a junior researcher at the SETI Institute. She noticed something odd about the signal's single recorded pulse. Its frequency curve matched the predicted profile of a targeted transmission, one deliberately compressed to minimize interstellar dispersion. In other words, it looked engineered to travel vast distances without degrading. Natural phenomena don't optimize themselves for efficiency, technology does. Today, Signal 12 remains a stain on the data, too strange to ignore, too elusive to prove. It forces us to confront an uncomfortable truth. The universe might be teeming with signals we can't reliably catch. Not because they're not there, but because they're playing by rules we don't yet understand. And sometimes the most profound messages aren't the ones that repeat. They're the ones that leave us guessing. Signal 13 didn't just whisper or shout, it painted the cosmos in every color of the spectrum. When astronomers first locked onto this transmission from Interstellar Comet 2026T4, they weren't just picking up radio waves. The comet was broadcasting across 5 distinct wavelengths simultaneously: radio, infrared, visible light, ultraviolet, and even faint X-rays. This wasn't just unusual, it was unprecedented. Cosmic objects specialize. Pulsars spin out radio beams, quasars blaze in ultraviolet, but Signal 13, it was a one-comet symphony. Each note played in perfect harmony across the electromagnetic spectrum. The moment observatories confirmed the multi-wavelength emission, the race was on to explain it. Natural cosmic phenomena rarely emit across such a broad range, and when they do, it's chaotic, like the scattered light of a supernova. Signal 13 was different. Each wavelength pulsed in sync, rising and falling together with eerie coordination. The radio waves hummed at 450 MHz while the ultraviolet spikes flared at precise 10-minute intervals like clockwork. Even more baffling, the ratios between wavelengths held steady, locked into mathematical constants that mirrored human-engineered broadcast systems. Coincidence? Maybe, but nature doesn't do coincidences this precise. Theories erupted like solar flares. One camp proposed an extreme version of synchrotron radiation, where electrons spiraling in a magnetic field emit across multiple wavelengths. But for that to work, the comet would need a magnetic field stronger than Jupiter's, packed into a nucleus barely 5 miles wide. Another team pointed to thermal cascading, where heat from the sun vaporized layered ices, each layer emitting at a different wavelength as it sublimated. The math almost worked until researchers realized the signal's infrared spikes were cooler than the comet's surface temperature. Energy doesn't flow backward. Then came the observation that shattered every assumption. When the Chandra X-ray Observatory analyzed the high-energy emissions, they found something impossible. The X-rays were inverse. Instead of scattering randomly, they concentrated into tight beams like a laser's reverse image. Natural X-rays don't focus, they spray, but they were directed. The implication was staggering. If something or someone was deliberately coordinating emissions across 5 wavelengths, it would require technology beyond our wildest dreams. Or a natural phenomenon we've never witnessed. As the comet streaked toward the outer solar system, Signal 13 did something even stranger. It began rotating its emissions. Every 27 hours, the dominant wavelength shifted radio to infrared, infrared to visible, cycling through the spectrum like a cosmic dial. No known celestial process behaves this way. Stars don't switch flavors, black holes don't toggle outputs, but this comet did. By the time it passed beyond Saturn's orbit, the transmission had rewritten the rulebook. Because here's the chilling truth, the universe doesn't just communicate in single wavelengths. Sometimes it speaks in every frequency at once, and we're only beginning to learn how to listen. Signal 14 didn't just transmit, it answered. When astronomers first detected this bizarre transmission from Interstellar Comet 2026U7, everything about it seemed ordinary. A steady pulse at 600 megahertz, flickering like dozens of others before it. But then, after exactly 42 minutes of silence, something impossible happened. The same signal returned not as a random echo, but as a perfect time-delayed copy. Every modulation, every dip and peak in the original transmission played back with pinpoint accuracy. It was as if the universe had pressed record, waited, and then hit replay. This wasn't just unusual, it defied physics. Natural echoes in space don't work this way. Radio waves scattering off plasma clouds or asteroid surfaces return distorted, fragmented, or not at all. Signal 14's echo, though, it was pristine, as if whatever bounced it back had memorized the original transmission and recreated it note for note. Teams at the Very Large Array in New Mexico ran simulations, testing every conceivable natural reflector, ionized gas trails, metallic asteroid fragments, even hypothetical quantum foam structures. Nothing could explain the precision. The echo's timing was too exact, its fidelity too perfect. Then came the chilling realization: the delay wasn't arbitrary. 42 minutes wasn't just a random gap, it was calculated. For the comet's distance from Earth at detection, 42 minutes was the exact round-trip time for light to travel from the comet to a hypothetical object positioned precisely at the solar system's edge and back. A mirror, in other words, but not a natural one. Natural mirrors like icy moons or dense plasma fields don't anchor themselves to orbital mechanics, they drift. They distort, they don't wait 42 minutes to reflect a signal with textbook precision. The implications split the astronomy community wide open. One faction argued for an ultra-rare gravitational lensing event where the comet's trajectory briefly aligned with a massive object, bending its own signal back toward us like a cosmic boomerang. But gravitational echoes smear, they stretch, they don't deliver crystal-clear replicas. Another team proposed a more unsettling idea. What if the comet wasn't generating the signal at all? What if it was passing through some kind of structure, a relic or device lurking in the outer solar system, silently recording and rebroadcasting anything that came its way? As the debate raged, Signal 14 did something even stranger. On its final observed cycle, the echo changed. Not much, just a single extra pulse appended to the end, like a postscript added to a letter. Then silence, no explanation, no follow-up, just that one subtle addition, as if whatever was out there had decided to leave a footnote. Today, the data sits in observatory archives, a riddle wrapped in a reflection. Because here's what keeps researchers awake. Echoes are supposed to fade, they're supposed to decay, but this one, it didn't just return, it responded. And in the grand silence of the cosmos, even the faintest reply can sound like a shout. Signal 15 didn't dazzle with complexity or shock with power, it baffled with sheer simplicity. While other interstellar comet transmissions pulsed, harmonized, or even screamed across the cosmos, this one did the opposite, nothing. Detected from Comet 2,026 V8, the signal was little more than a pure, unmodulated carrier wave, a single, unbroken tone at 512 MHz with no variation, no pulses, no hidden patterns. Just a monotone hum, like a dialed tone from the depths of space, and that very absence of complexity, that's what kept scientists up at night. In the realm of radio astronomy, simplicity is often the hardest thing to explain. Natural cosmic radio sources are messy by default. Solar flares crackle with static, pulsars stutter with interference. Even the faint whisper of the cosmic microwave background ripples with microscopic variations. A perfect, unchanging carrier wave doesn't just defy expectations, it defies physics. There's no known natural process in the universe that generates a radio signal this clean. Not stellar winds, not magnetized plasmas, not even the eerie vibrations of spacetime itself. The moment observatories locked onto Signal 15, the hunt for explanations began. One team proposed an ultra-stable cryogenic maser, a theoretical scenario where the comet's icy interior, laced with ammonia or methanol, could act like a natural laser, amplifying a single frequency with unnatural precision. But masers require specific energy inputs, and the comet's frozen nucleus showed no signs of the intense internal heating needed to sustain one. Another group pointed to Schumann resonance, where electromagnetic waves might theoretically bounce between a comet's surface and its ionized coma. Yet Schumann resonances on Earth are anything but pure. They're noisy, fluctuating, and riddled with harmonics. Signal 15 had none of that. It was sterile. Then came the observation that turned intrigue into unease. Over 72 days of continuous monitoring, the signal's frequency never drifted, not by a fraction of a hertz. For a comet hurtling through space at tens of thousands of miles per hour, bombarded by solar wind and gravitational tugs, this level of stability was statistically impossible. Doppler shifts alone should have nudged the frequency up or down as the comet's velocity changed, yet the tone remained frozen, as if anchored to some invisible cosmic metronome. Theories veered into uncharted territory. Could the comet be housing an artificial oscillator, some relic or device designed to emit a reference signal like a cosmic tuning fork? Human spacecraft use similar beacon modes for navigation, broadcasting steady tones to help ground stations track their position. But this wasn't just a fleeting whisper. Signal 15 endured for months, its unbroken hum defying entropy itself. By the time the comet retreated beyond Neptune's orbit, the signal had rewritten the rules. Because here's the paradox haunting every researcher who studied it. In a universe built on chaos and noise, perfection is the rarest anomaly of all. And sometimes the most unsettling message isn't a pattern or a pulse, it's the silence between them. Signal 16 didn't just drift or modulate, it leaped. While other interstellar comet signals shifted frequencies gradually or pulsed in predictable patterns, this one rewrote the rules in real time. Midway through its transmission, as astronomers at the Green Bank telescope were carefully tracking its steady 600 MHz hum, something impossible happened. Without warning, the signal jumped not by a few kilohertz, as Doppler shifts might cause, but by a staggering 200 MHz in less than a millisecond. One moment a stable tone, the next a completely different frequency, as if someone had flipped a cosmic switch, and then, just as suddenly, it leaped back. Frequency jumps like this aren't just rare, they're unheard of in natural cosmic phenomena. The closest earthly analogy would be a radio station abruptly changing its broadcast channel mid-song, then switching back seconds later. But nature doesn't work that way. Solar flares ramp up chaotically, pulsars spin down predictably. Even the most violent astrophysical events, supernova, magneta bursts, don't produce instantaneous, precise frequency hops. This wasn't turbulence, this wasn't interference, this was discontinuity, a break in the laws of physics as we know them. Researchers scrambled for explanations. The leading theory involved an unimaginably violent magnetic snap, a scenario where the comet's internal magnetic field, stressed by solar wind pressure, suddenly reconfigured itself, briefly altering the resonant frequency of its emissions. But simulations quickly exposed the flaw. Magnetic reconnection events, even the most extreme ones, take time seconds or minutes, not milliseconds. Another team proposed a plasma echo chamber model, where charged particles in the comet's tail briefly formed a new reflective surface, shifting the signal's apparent frequency. Yet plasma doesn't reconfigure itself with this kind of razor precision. The real curveball came when astronomers noticed the jumps weren't random. Over 6 observed leaps, the frequency shifts followed a hidden pattern. Each new landing point was an exact harmonic of the original signal, as if the comet were cycling through preset channels. Nature doesn't do preset channels, technology does, communication systems do. The implications were impossible to ignore. Either we'd stumbled upon a freakish new class of astrophysical behavior, or something inside or behind. That comet was making deliberate adjustments. As the debate raged, Signal 16 added one final twist. On its last observed transmission, the jumps accelerated, flipping between frequencies faster than the telescopes could track. Then, in a blink, it was gone, leaving behind a trail of scorched logic and an unsettling question. When the universe changes its tune that abruptly, who or what is holding the dial? Signal 17 didn't crackle, pulse, or dance across frequencies, it thrummed. While other interstellar comet transmissions came and went in flashes of complexity, this one settled into the background like the deep, resonant hum of a distant engine. Detected from Comet 2027W2, the signal was almost easy to miss at first, a faint, unchanging vibration at just 47 Hz, so low it skirted the edge of what radio telescopes could detect. But as days turned into weeks, astronomers realized this wasn't some fleeting anomaly. The hum persisted, unwavering, long after the comet had sailed past Jupiter's orbit. And that consistency, that stubborn refusal to fade, posed a question no one could easily answer. What in the cosmos could generate a sound this patient? The signal's ultra-low frequency immediately ruled out most conventional explanations. Solar wind interactions typically produce emissions in the kilohertz or megahertz range, not the subsonic depths where Signal 17 resided. Cometary outgassing, usually a chaotic spray of radio static, couldn't account for the hum's eerie stability. Even the vibrations of the comet's nucleus stretching and compressing as it tumbled through space should have produced fluctuations. Yet the hum held its pitch like a tuning fork struck in a vacuum. The leading theory pointed to interstellar plasma, the thin, electrified gas that fills the void between stars. As the comet plowed through this invisible ocean, its magnetic field, however weak, might have stirred up waves in the plasma, like a ship's wake rippling through water. Under the right conditions, those waves could theoretically resonate at ultra-low frequencies, generating a hum detectable across light years. It was an elegant idea, but the math had holes. For one, the signal's intensity was orders of magnitude stronger than any predicted plasma interaction. For another, the hum's purity defied the messy reality of space where turbulence, magnetic fields, and particle collisions should have distorted it beyond recognition. Then came the observation that upended everything. When researchers cross-referenced Signal 17 with data from NASA, a Voyager probe's humanity's farthest-flung ambassadors to interstellar space, they found something unsettling. The hum's frequency matched oscillations recorded by Voyager 1 as it crossed the heliopause, the boundary where the sun's influence wanes and interstellar plasma takes over. Coincidence, maybe, but the odds of two unrelated phenomena producing identical frequencies in the same patch of cosmic wilderness were astronomically low. The implications were staggering. If the hum wasn't coming from the comet, but through it, if the comet was merely acting as a conduit for some larger interstellar vibration, then we weren't just listening to a wandering iceberg. We were eavesdropping on the cosmos itself, a whisper from the void resonating across light years, and the most haunting part, we still don't know what's speaking. Signal 18 didn't just transmit, it counted in a language we almost recognized. When astronomers first isolated this transmission from Interstellar Comet 2027X5, the pattern seemed innocuous, short pulses alternating with long ones, flickering at irregular intervals. But then a junior researcher at the Max Planck Institute noticed something chilling. The intervals weren't random, they mapped precisely to binary code. Not just any binary, but a repeating 8-bit sequence 00110101, repeating in cycles of exactly 19 minutes. For the first time in history, a cosmic signal wasn't just puzzling scientists, it was speaking their own technological tongue. The moment the binary pattern emerged, the astronomy community fractured. Optimists pointed to the sequence's eerie resemblance to error-checking protocols used in early space missions, a way to ensure data integrity across noisy channels. Skeptics fired back with cold logic. Nature loves patterns, and binary is just another one. After all, the universe runs on simple mathematical rules, ones and zeros baked into the fabric of reality itself. But the real controversy wasn't the code's existence, it was its persistence. Over 14 days of observation, the sequence repeated 432 times without a single deviation, a statistical anomaly bordering on impossibility for any known natural process. Mainstream astronomers scrambled for non-alien explanations. One team proposed magnetic bit flipping, where the comet's rotation periodically aligned iron-rich minerals with the sun's magnetic field, generating pulses that mimicked binary through sheer coincidence. Another group suggested thermal cracking, a scenario where stress fractures in the comet's icy shell opened and closed like cosmic Morse code keys, but simulations revealed fatal flaws. Magnetic interactions couldn't sustain the pattern's precision across weeks. Thermal fractures wouldn't produce pulses this clean. Then came the skeptics' knockout punch. When linguists analyzed the sequence using cryptographic tools, they found something unsettling. The 8-bit blocks weren't just repeating, they were checksummed. Every fourth transmission included an extra pulse, a redundancy resembling parity bits in human-designed error correction. Natural processes don't invent error checking. Machines do, networks do. The revelation sent shockwaves through SETI circles, reigniting debates about technosignatures, hallmarks of technology embedded in cosmic noise. Yet for all the excitement, the signal refused to conform to expectations. On day 15, without warning, the sequence inverted. Ones became zeros, zeros became ones, as if some cosmic switch had flipped. Then 12 hours later, it reverted to the original code before vanishing entirely. No fading, no distortion, just silence where there had once been a conversation. Today, Signal 18 remains a Rorschach test for the scientific community. To some, it's proof that math is universal, a pattern so fundamental even comets stumble into it. To others, it's a ghost in the machine, whispering that we might not be the only ones counting in the dark. But perhaps the most unsettling truth lies in the middle. Whether natural or not, the universe just handed us a mirror. And the reflection is uncannily familiar. Signal 19 didn't just fade, it collapsed. Unlike the steady hums or erratic bursts of previous interstellar comet transmissions, this one pulled off a cosmic magic trick, vanishing in plain sight. When astronomers first detected it from Comet 2027Y6, the signal blazed across a staggering 500 megahertz of bandwidth, a chaotic, roaring static that resembled the aftermath of a supernova. But then, over the course of just 12 days, something impossible happened. The bandwidth began to shrink, not randomly, not in fits and starts, but with methodical precision, like a funnel tightening around the signal's throat. By the time it vanished, the transmission occupied a sliver of its original spectrum, a mere 5 kilohertz, so narrow it could have been mistaken for a human radio station. And that left scientists staring at the data, asking one terrifying question: since when do cosmic signals optimize themselves? The vanishing bandwidth defied every known natural process in radio astronomy. Cosmic phenomena don't clean up their emissions. Solar flares spray energy indiscriminately. Pulsars scatter their beams. Even the most structured astrophysical events, like magnetar eruptions or black hole jets, don't suddenly decide to broadcast on a single frequency. Yet Signal 19 did exactly that, compressing its output with surgical precision. The leading theory pointed to an ultra-rare plasma lensing effect where the comet's ionized tail, heated by the sun, acted like a natural filter, progressively blocking all but the strongest frequencies. But simulations quickly unraveled. Plasma lenses distort, they scatter. They don't sculpt a signal's bandwidth with micrometer accuracy. Then came the observation that shattered expectations. As the bandwidth narrowed, the signal's strength didn't diminish, it intensified. Like a whisper sharpening into a scream, the transmission concentrated its energy into that shrinking sliver of spectrum, defying the laws of entropy. Energy doesn't behave this way in nature. It dissipates, it spreads. It doesn't spontaneously rally into a laser focus. That kind of precision is the hallmark of engineering, of systems designed to maximize efficiency over distance. Human deep space probes use similar bandwidth compression to punch signals through interstellar noise. Was this comet mimicking our own technology, or was something else at work? The final twist came in the signal's last hours. Just before it winked out, the bandwidth hiccuped, expanding momentarily by exactly 2 kilohertz, then snapping back. A glitch, a fluctuation, or something more unsettling, a correction. Natural processes don't recalibrate. Machines do. Networks do. The universe isn't supposed to tidy up its own noise. Yet here we were, watching it do exactly that. By the time the comet slipped beyond observational range, Signal 19 had left behind a paradox wrapped in static. A transmission that didn't just defy physics, it refined it. And that raises a chilling possibility. What if some signals aren't just cosmic accidents? What if they're learning? Signal 20 didn't just pulse, it breathed. While other interstellar comet transmissions crackled with chaos or hummed with mechanical precision, this one moved with an almost organic rhythm. Detected from Comet 2027Z7, the signal arrived as a series of bursts, each one perfectly mirrored by an identical pulse exactly 1 minute and 18 seconds later. Not roughly, not approximately, exactly. The symmetry was so flawless it felt less like a cosmic accident and more like a metronome ticking in the void. At first glance, symmetry isn't unusual in nature. Snowflakes branch in fractal patterns, planets orbit in elliptical harmony, but radio emissions, they're messy. Unpredictable, governed by the turbulent interplay of magnetic fields and charged particles. For a signal to pulse with this level of mirrored precision, something extraordinary had to be at work. Researchers scrambled to model plausible explanations. One team proposed a double-lobed comet nucleus, a dumbbell-shaped core spinning in such a way that solar wind struck each lobe in perfect alternation, generating paired radio bursts. Another group suggested a magnetic pendulum effect, where the comet's internal magnetic field oscillated between two stable states, triggering emissions like a cosmic seesaw. But the math refused to cooperate. For the double-lobed theory to hold, the comet's rotation would have needed to sync perfectly with solar wind pressure, a balancing act so delicate even the slightest perturbation would have shattered the symmetry within hours. Yet Signal 20 maintained its mirrored pulses for 37 days without deviation. The magnetic pendulum idea fared no better. Simulations showed that any natural oscillation would have decayed over time, the pulses growing increasingly erratic as energy dissipated. Instead, the signal held its rhythm like a Swiss watch, utterly indifferent to the chaos of space around it. Then came the observation that tipped the scales. When astronomers analyzed the pulse shapes, they found something even more unsettling. Each burst wasn't just timed symmetrically, it was shaped symmetrically. The leading and trailing edges of every pulse were mirror images, rising and falling in mathematically identical curves. Natural radio bursts don't do this. They spike and crash asymmetrically, jagged with interference. Only engineered signals like human radar or communication pulses exhibit this kind of pristine symmetry. The discovery split the astronomy community. Was this nature's most elaborate coincidence, or evidence that symmetry in the depths of space isn't always accidental? As the comet retreated beyond observational range, Signal 20 left behind a haunting lesson. The universe adores patterns, but some patterns feel less like cosmic artistry and more like signatures. And the deeper we listen, the harder it becomes to tell the difference. Signal 21 didn't just drift, it streaked across the spectrum. When astronomers first locked onto this transmission from Interstellar Comet 2028 at 8, the signal seemed ordinary enough, a steady pulse at 700 MHz humming along like so many before it. But within hours, the tone began to slide, plummeting toward lower frequencies at a rate that defied all expectations. This wasn't the gentle Doppler drift of a comet cruising through space, it was a headlong dive, as if the source were accelerating toward us at impossible speeds. By the time the signal faded 72 hours later, its frequency had dropped by a staggering 200 MHz, a shift so extreme it implied velocities no natural object should achieve. The moment the data registered, observatories worldwide sounded the alarm. Doppler shifts are commonplace in astronomy. Stars, planets, even galaxies exhibit them as they move toward or away from us. But Signal 21's shift was violent. To produce a drop that dramatic, the comet would have needed to accelerate from a relative crawl to a significant fraction of light speed in mere days. And that was impossible. Comets don't have engines, they coast on gravity's whim, their trajectories bending lazily around stars and planets. Yet the signal's nosedive suggested something else entirely, a force acting on the comet, or perhaps on the signal itself, with physics-shattering intensity. Theories erupted like solar flares. One faction pointed to an unseen companion, a hidden black hole or neutron star tugging the comet into a sudden hyperbolic trajectory. But deep field surveys found no such object along the comet's path. Another team proposed a plasma wake scenario where the comet plowed through an unusually dense interstellar cloud, its charged tail acting like a cosmic sail caught in a particle wind. Simulations showed promise until researchers realized no known cloud could impart that much acceleration without tearing the comet apart. Then came the observation that rewrote the playbook. When astronomers cross-referenced the signal's frequency drift with the comet's actual velocity measured independently via optical telescopes, the numbers didn't match. The shift was too extreme, implying motion that outstripped the comet's observed speed by orders of magnitude. That left only two possibilities. Either our understanding of Doppler physics was fundamentally flawed, or the signal wasn't coming from the comet at all, but from something near it, something moving at relativistic speeds. The implications were staggering. If the signal source wasn't anchored to the comet's nucleus, what was generating it? A probe, a relay, or something even more exotic, a fragment of alien technology slingshotting past our solar system, its transmissions warped by velocities we can barely comprehend. Signal 21 vanished as abruptly as it appeared, leaving behind a trail of shattered assumptions and one indelible truth. In the cosmic dark, even the laws of motion might not be what they seem. And sometimes the most profound messages aren't in the signal but in how it moves. Signal 22 didn't just vanish, it erased itself from the record. Unlike the rhythmic pulses or haunting hums of previous interstellar transmissions, this one arrived with a singular, unrepeatable burst of complexity, then disappeared forever. Detected from Comet 2028b9, the signal exploded across radio telescopes for exactly 94 seconds, a dazzling tapestry of overlapping frequencies, shifting modulations, and nested mathematical patterns unlike anything witnessed before or since. And then silence, no echoes, no follow-ups, just a void where brilliance had been. What made Signal 22 so maddening wasn't just its uniqueness, it was the sheer impossibility of studying it. In astronomy, rare events can still be analyzed through repetition. A supernova might occur once a century, but we've catalogued thousands. Even bizarre cosmic phenomena like fast radio bursts recur often enough to build theories. But this, a one-time burst of organized chaos, it was like trying to reconstruct a symphony from a single note. Teams at the Very Large Array and the Square Kilometre Array Consortium scrambled to capture every possible detail during those fleeting seconds, but the signal's complexity overwhelmed their systems. It wasn't just broadband, it was omniband, emitting across the entire detectable spectrum simultaneously, yet somehow maintaining distinct, coherent structures within the noise. Theories collapsed under scrutiny. One group proposed a cosmic lightning strike, a hypothetical event where the comet's magnetic field briefly reconfigured into a natural maser, amplifying random solar radiation into a structured pulse. But masers don't produce layered signals. Another team suggested a collision. Perhaps the comet had grazed an ultra-dense dark matter filament, triggering a one-time particle decay cascade visible across wavelengths. Yet dark matter doesn't announce itself in radio waves. The wildest hypothesis came from a rogue astrophysicist at Harvard. Could the comet have passed through a wormhole's mouth, its signal warped by space-time curvature into a transient burst of artificial-seeming complexity? Even she admitted it was less science and more desperation poetry. The cruelest twist came in the aftermath, when observatories reviewed their archives for similar signals, even fragments, they found nothing. Not a whisper, not a shadow. It was as if the universe had staged a meticulously rehearsed performance for an audience of telescopes, then burned the script. Today, Signal 22 exists as a cosmic flare in the data, a reminder that some mysteries refuse to be solved. Because here's the truth that keeps astronomers uneasy: the universe isn't just hiding secrets. Sometimes it shows them to us once, just long enough to prove we're not as clever as we think. Signal 23 didn't just emit, it orchestrated. While most cosmic radio sources blast out noise or settle into monotonous tones, this transmission from Interstellar Comet 2028c10 arrived as a shimmering constellation of frequencies, each one perfectly tuned to the others. Not a single note, but a chord, a cluster of 7 distinct radio waves, all harmonically linked in ratios that mirrored the intervals of a musical scale. 600 MHz, 400, 300, 200, each frequency a clean mathematical division of the one before it. This wasn't just unusual, it was unheard of. Nature doesn't compose symphonies, yet here was a comet humming one into the void. The harmonic structure alone would have been remarkable, but Signal 23's behavior elevated it to the realm of the uncanny. The frequencies didn't just coexist, they interacted. When the primary tone at 600 MHz fluctuated, the others adjusted instantaneously, maintaining their precise ratios as if bound by an invisible conductor. Solar wind should have scrambled this delicate balance, magnetic fields should have warped it, yet the harmony held note perfect for 29 days. Scientists ran simulations, searching for any natural process that could lock multiple frequencies into such rigid synchronization. The closest match, human-made synthesizers, electronic instruments designed to generate harmonic overtones. The universe, it seemed, had just handed us a cosmic keyboard. Theories splintered under the weight of impossibility. One team proposed a resonant cavity model, a scenario where the comet's icy interior, laced with metallic minerals, formed a natural chamber that amplified specific harmonics. But cavities don't sustain precision across weeks of solar heating and rotation. Another group pointed to plasmonic oscillations, where charged particles in the coma vibrated at mathematically related frequencies. Yet plasmas are turbulent, their oscillations smear into noise, not crystalline chords. Then came the observation that shattered every assumption: the harmonics weren't static. Every 47 hours, the cluster transposed, shifting all 7 frequencies upward by exactly 78 MHz, like a musician changing key. Natural processes don't follow sheet music. They don't obey rules of musical theory, but Signal 23 did. And when it finally faded, it didn't decay or distort, it resolved, the harmonics collapsing back into a single tone as if ending a performance. The cosmos has whispered many secrets, but this wasn't a whisper, it was a melody, and the most haunting question isn't what composed it, but why. Signal 24 didn't just speak, it listened. While earlier interstellar comet transmissions pulsed or hummed in isolation, this one did something unprecedented. It echoed. Not the faint, distorted reverberation of a signal bouncing off a distant asteroid or plasma cloud, but a crisp, near-perfect copy of itself returning from the depths of space, delayed by precisely 1 hour, 7 minutes and 22 seconds. As if something out there, impossibly far beyond the comet's trajectory, had caught its whisper and thrown it back. The moment astronomers at the Deep Space Network picked up the echo, the hunt for explanations began. Natural echoes in space are rare, but not unheard of: ionized gas clouds, metallic debris fields. Even the turbulent edges of planetary magnetospheres can reflect radio waves. But those reflections are always messy, smeared by interference and Doppler shifts. Signal 24's echo was pristine. Every modulation, every subtle dip and peak in the original transmission, played back with near-identical fidelity, just quieter, as if the returning signal had traveled through an unfathomable distance. Theories immediately split into 2 camps. The first clung to natural explanations, proposing an ultra-dense interstellar mirror, a hypothetical structure like a rogue metallic asteroid or a fragment of a neutron star's crust drifting in the void, its smooth surface reflecting the signal like a cosmic billiard ball. But calculations revealed a problem. For an object to reflect with such precision at that distance, it would need to be impossibly large, perfectly flat, and aligned with millimeter accuracy. The odds of such a structure existing, let alone being positioned exactly where needed, were beyond astronomical. The second camp ventured into stranger territory. Could the echo's timing, 1 hour, 7 minutes, 22 seconds, hold a clue? When researchers converted the delay into distance, accounting for light speed lag, the math pointed to an object roughly 640 astronomical units away, far beyond Pluto's orbit, in the frozen reaches where the sun's influence wanes. Coincidentally, that placed the reflector near the theorized inner edge of the Oort cloud, a shell of icy debris surrounding our solar system. But here's what sent chills down spines: the timing wasn't arbitrary. The numbers aligned too neatly with the comet's own velocity and trajectory, as if the echo was synchronized. Then came the observation that rewrote the rules. Midway through the signal's 3-week lifespan, the echo changed. Not in timing or frequency, but in polarity. The reflected waves flipped orientation, as if the mirror had suddenly become a phase inverter. Natural reflectors don't do this. Rocks don't tweak physics on the fly. Yet something out there wasn't just bouncing the signal back, it was altering it. The implications were staggering. Either we'd stumbled upon a freakish new class of astrophysical object, or the echo wasn't an echo at all. Was it a relay? A probe, or something even more unsettling, a response? By the time the comet slipped beyond observational range, the echo had faded into silence, leaving behind a single, haunting truth. Sometimes the universe doesn't just send messages. It answers, and the answer, it seems, is still echoing through the dark. Signal 25 didn't just defy expectations, it rewrote the rulebook entirely. Of all the unexplained transmissions from interstellar comets, this one stands apart, not just for its complexity, but for how effortlessly it shattered every assumption scientists had built over decades of study. Detected from Comet 2,028d11, the signal arrived as a paradox wrapped in static, a transmission that was simultaneously too structured to be natural yet too alien to be artificial. Its opening act alone was enough to send observatories into chaos, a rapid-fire sequence of pulses that spelled out, in flawless prime number intervals, the first 6 digits of pi. Not approximately, not coincidentally, exactly. What followed was even stranger. After its mathematical overture, the signal split into 3 parallel streams, each operating on a different frequency, each modulating independently, yet all harmonizing in a way that resembled a 3-part fugue more than any cosmic phenomenon. One stream maintained a steady carrier wave, humming at 420 MHz with the precision of an atomic clock. Another wove intricate bursts of binary-like code, repeating in cycles that mirrored Fibonacci sequences. The third, pure noise, a hissing, chaotic static that, when analyzed, contained fractal patterns repeating at scales no natural process should produce. Together, they formed a transmission that felt less like a signal and more like a conversation, one where each voice spoke a different language, yet somehow belonged to the same sentence. Theories collapsed almost as quickly as they formed. The natural resonance camp pointed to the comet's unique composition, a cocktail of exotic ices and metals that, under solar heating, might create overlapping resonant cavities. But no known material could sustain 3 separate emissions with such precision, let alone coordinate them into a cohesive whole. The technological artifact faction had more traction but faced its own existential hurdle. If this was a designed signal, its architecture bore no resemblance to human engineering. Our most complex deep space probes use multiplexing to transmit on multiple frequencies, but their streams are tightly synchronized, not elegantly divergent. Signal 25 streams felt organic, as if grown rather than built. Then came the knockout punch. Midway through its month-long broadcast, the signal did something no natural phenomenon should ever do. It adapted. The chaotic third stream, the fractal noise, suddenly cleaned up, its randomness resolving into a repeating pattern that mirrored the first stream's carrier wave. It was as if the transmission had been listening to its own echo and decided to harmonize. Natural processes don't self-correct. Solar flares don't smooth out their static. Pulsars don't adjust their spin to match neighboring stars, yet here was a signal that seemed to learn. By the time the comet retreated beyond observational range, Signal 25 had left behind more than just data. It had rewritten the questions. Not what is this, but what understands us, because the truth is we're no longer just listening to the universe, we're being listened back to, and the most unsettling part isn't the mystery. It's the creeping suspicion that we're not the ones being tested. We're the answer, From the rhythmic pulses of signal 2 to the harmonic symphony of signal 23, these 25 transmissions have done more than just crackle through our telescopes. They've rewritten the rules of what we thought possible. Each one stands as a cosmic riddle, defying explanation in ways that oscillate between unnerving and exhilarating. Signal 5 screamed into the void with the force of a dying star, while Signal 15 hummed a single, unbroken tone for months of perfection in a universe built on chaos. Signal 8 twisted its waves into spirals like a radar pulse, and Signal 18 counted in binary as if speaking our own language back to us. And then there's Signal 25, the grand finale, a transmission so layered it felt less like a message and more like a conversation waiting for a reply. What ties these mysteries together isn't just their strangeness, it's how they expose the gaps in our understanding. For every natural explanation that almost fits, there's a detail that shatters it, signals that adapt, frequencies that leap, echoes that return too precisely. These comets aren't just icy wanderers, they're cosmic enigmas hinting at physics we haven't discovered, or worse, technologies we can't yet comprehend. Whether it's plasmas behaving impossibly or patterns too clean to be accidental, one thing's clear: space is stranger than we've dared to imagine. Now we turn to you. Which of these signals unsettled you the most? Was it the mathematical precision of Signal 10, counting prime numbers into the dark, or the eerie evolution of Signal 19, compressing itself like a machine optimizing its own broadcast? Drop your theories in the comments, because in a universe full of whispers, sometimes the most thrilling part isn't finding answers. It's realizing how many questions we've yet to ask. And if you're hungry for more cosmic mysteries, hit subscribe. The universe isn't done talking, and neither